Hello and welcome to the session. In today's session, we'll be using dynamic programming to solve a typical problem called matrix chain multiplication. Now, dynamic programming is one of the interesting domain of computer science, which has been used in addressing many problems. But what are the characteristics of those problems which can be addressed through dynamic programming? Well, for that, the first thing we need to learn is the principle of optimality. Now, look into the principle of optimality slide. Dynamic programming follows the principle of optimality. Now, what is this principle then? The principle of optimality is that components of a globally optimum solution must themselves be optimal. So let us read it again. There is a solution, global solution, right? So you have reached a solution and components of those solutions are optimal by themselves. So there is a solution, optimal solution existing in this particular case. So this principle of optimality is about a global solution will be optimal only if all the components of it are also optimal. Let's take an example of this situation. And the example for this we have selected for the time being is the shortest path problem that satisfies the principle of optimality. Now, consider an example where there is a path from A to B and the optimal path passes through x1, x2 till xn till B. So there is a path from, and suppose this is the shortest path from node A to node B in a graph. Then the portion of x1, xi to xj, right? So any xi, maybe x2 to xn minus 1, right? Xi to xj, that is any path, any subpath of that path is shortest path for xi to xj. So select any of the subpaths and that should be optimal. Right? So this is a very important consideration or important point which you must understand as far as principle of optimality is concerned. So given a solution which we are saying is an optimal solution, all the components of that optimal solutions should also be optimal, but in the sequence only, right? Xi to xj are in a particular sequence. So if it is x1, x2, x3, that may be optimal if it is falling in the path from A to B, the optimal path of A to B. Now, a problem has an optimal substructure if an optimal solution can be constructed efficiently from the optimal solutions of its subproblems. So we need to construct an optimal solution. Now, how it is related to dynamic programming? So principle of optimality is fine, but how is it related to dynamic programming? So dynamic programming primarily develops a mathematical notation that can express any solution and sub-solution for that problem. So basically problem as well as its sub-problems. Now it looks abstract, but as we go towards the problem solution, you will be clear about this particular concept. It proves that the principle of optimality holds. So if you are applying dynamic programming, you have to prove that the principle of optimality applies for that. Otherwise, whatever solution you will be developing through dynamic programming may not be optimal as far as sub-solutions are concerned, and it may not be an optimal solution. It is not guaranteed to be an optimal solution. And what we do here is we develop a recurrence relation that relates a solution to its sub-solutions and identify the term that signifies the final solutions. Now, if you can consider the recurrence when you were calculating factorial, right? So factorial, we develop a recurrence relation of the kind fn equals to fn minus 1 multiplied by n itself. And the terminating condition is when n equals to 1, the factorial n becomes 1. So like that, in dynamic programming also, you got to develop a recurrent relation. Okay. Then you write an algorithm to compute the recurrence relation. And when the principle of optimality holds, dynamic programming based solutions are guaranteed to yield an optimal solution. And luckily, no proof of optimality is needed in this particular case. Why? Because we are guaranteed to get the optimal solution. So you need not do this exercise of proving that this solution is going to be optimal. You just prove that it is basically following the principle of optimality. Now, what is matrix multiplication? So these are the two things we will be using. That is, we will be using dynamic programming as a method for solving the problem. But what problem are we attempting through dynamic programming? So let us try to define that particular problem. And that problem, what we are trying to say, let's first identify what do we mean by matrix multiplication, although you know it, but let's define the mathematical connotation of it. Okay? So, matrix multiplication is a binary operation, first of all. It's not a ternary or any, it's just a binary operation. That means you are multiplying two matrices at a time only. Okay? It can be performed if matrices are conformable for multiplication. What do we mean by conformable? If matrices A and B are of order P and Q, P cross Q, and S cross T, then Q equals to S. Has to be there. Q should be equals to S. Okay. Would be conformable for A cross B, A multiplication B, only if when Q, this Q is same as S. All right. Otherwise it won't be. And if you want to multiply B cross A, right, then the T, okay, T and P should be equal. So these are the condition for conformability. The dimension has to be the same. All right. Then only you can multiply. Then a very important property here is matrix multiplication is associative. Now, what we are trying to say here is if A, B and C matrices are of order M cross N, N cross P and P cross Q, so you can see that they are conformable. A, B, C are conformable, so we can multiply. Now there are two ways we can multiply them using in a associative way. That is AB, we multiply A and B first, and then the product of AB, which is going to be M cross P, we multiply with the second C matrix. Or we multiply BC first and then multiply with A. Right? So these are the two ways by which we can multiply them. Luckily for us, this multiplication is associative. So they are equal. And the product, final product is going to be of the order M cross Q. That is what you can see here. Matrix multiplication is not commutative. Unfortunately, it is not going to happen. If A and B have dimension M cross N and N cross P, and M is not equals to P, then matrix BA cannot be defined, right? AB can be defined because it is conforming, right? Conformable. But BA is not conformable because M is not equals to P. Therefore, they are not commutative. Now, this is a very, very important property. And what we are basically concerned with, what we are left with is associative property, and we will be using associative property. But how we are going to multiply a sequence of matrices. But before that, let's try to understand what are the complexity as far as matrix multiplication is concerned. So the number of scalar multiplication which while multiplying two matrices are very, very important term. In fact, this is what we use in defining, we use for multiplying the matrices, right? So scalar multiplication, this is what is going to define the complexity. It is the costliest operation as far as matrix multiplication is concerned. So number of multiplication is defining property. Remember that. Multiply A of, so I'm just showing you an example that there are two matrices here, A of dimension 3 cross 2 and B of dimension 2 cross 1. So that is M, N, and N and P. That's what we had considered. Okay. So if this is our matrix. Matrix 1 is, you see, first row, second row, and third row, right? That is how it is 3 cross 2. And the second is 2 cross 1. So 2 rows, single column. Okay. So when we are multiplying, how we are multiplying? 1, 2 will be multiplied by 7 and 8. 1 multiplied by 7 plus 2 by 8, forming the first column, right, of the result, which is 23. Like that, 3, 4 with 7, 8, forming the second row, and third row, like that. So how many multiplication in all? If you see, 3 into 2 into 1. 3 multiplication. Why? Because there are 3 rows, and we are multiplying 3 rows with 1 column. So 3 into 1, in any case 3 into 1 have to be there, and in each multiplication we are having 2 such multiplication, which is same as this particular number. So in effect we have 3 into 2 into 1. That is what is the total number of multiplication, and that is what is going to determine our complexity. So in this particular case, it turns out to be 6. So if we are multiplying 2 matrices A and B of order M cross N and N cross P, then we will require M cross N cross P scalar multiplication operation. And this is a very important, very important property, because this is what we would be using in our matrix multiplication or whatever chain matrix multiplication problem definition later on. Okay, now moving from here, what is the complexity as far as when we are multiplying a number of matrices? It's not complexity. What are the ways how you are going to multiply more than one matrices in a series? So suppose A cross B cross C. I want to multiply 3 matrices. So should I perform A cross B or B cross C? Will it make any difference? So let us explain this particular concept with the help of another example. So what we know, or what we have studied just now, that matrix multiplication is an associative operation, right? And the number of scalar multiplication may vary significantly depending on how we multiply matrices and their product matrices to get the final product. Let's explain this with the help of example. Consider 3 matrices. The order of A is 100 cross 10. Order of B is 10 cross 50. And order of C is 50 cross 5. So now if I want to multiply A cross B cross C, either I'll do A cross B multiplied by C, right? So if I do A cross B, what are the term? How many multiplication? 100 into 10 into 50. That is what is being produced here, right? Which is 50,000 computations. 50,000 computation in that sense of multiplication. So 50,000 multiplications. And order of A cross B, the resultant is going to be 100 cross 50. So that is what we are going to get. In the next step, we will multiply this particular result of 100 cross 50 with C. So which will require 100 into 50 into 5, right? So these are going to be 25,000 computations or multiplication. And the overall final order of this particular A cross B cross C is 100 into 5. Obviously 100 into 5. That is how you have multiplied. It's a chain of multiplication, right? So total you have got is 75,000 multiplications are required. If I compute using A cross B first, and then multiply the result of A cross B with C. On the other hand, if I do this computation A cross B cross C by first multiplying B cross C, okay, which will require, now B cross C will require 10 into 50 into 5, right? So just 2,500 computations, all right. And order of B cross C is going to be 10 into 5 only, this 10 and this 5. So next multiplication, this 10 into 5 and 100 into 10. So we are going to get 100 into 10 into 5, which are 5,000 computation. So order of A cross A multiplied by B cross C in a bracket is overall 100 into 5. That is what is the order of the earlier case also. But total number of multiplications are just 7,500. You can compare 75,000 with 7,500. So selecting a particular bracket, right, parenthesizations, as far as matrix multiplication is concerned, right, is very, very important. When you are multiplying two matrices, not two, just more than two matrices, then how you are going to multiply them, right? How you are going to parenthesize them. Which of the two you will multiply first and then the next one, right? Remember one particular thing, this is a chain of multiplication only, right? So you have to do parenthesization only, right? And you can't just convert any order. You cannot just do B cross A first like that. You cannot do that, right? You have to do A cross B cross C. You can multiply B cross C first and then with A, but in that sequence only. That is A cross result of B cross C. So like that you can do. But this chain is going to be maintained. A cross B cross C cross D, like that. Now, unfortunately, when you are doing this chain multiplication, so what is that problem? Let's try to define that problem of matrix chain multiplication. What is that problem? So given a sequence of conformable, very important, matrices for multiplication, select the optimal pairs of matrices in every step such that the overall cost of multiplication is minimal. All right. So this is what we want to do. We have to, in fact, parenthesize those matrix multiplication, because matrix multiplication is a binary operation. So given a chain, we can pick any two which basically are giving us minimal effect overall. Now, how do we select it? Right? So that is the spirit. So for a conformable sequence of n matrices, different ways of selecting matrix pair for multiplication grow exponentially. Unfortunately, it is moving towards NP-hard direction. Although it is not NP-hard, but it is, as the number of combinations will grow exponentially, as the number of matrices which are to be multiplied will grow exponentially. So the problem size will grow exponentially. Therefore, we got to do some good things, and dynamic programming is going to help us out in this particular doctrine. The problem is not actually performing the multiplication. Remember this, but deciding the order to perform the multiplication. So it is going to be in what order we are going to perform the multiplication so that the problem overall multiplication is performed in the fastest way. So this matrix chain multiplication problem basically decides the parenthesization, right, in a way that what pairs of matrices should be multiplied in what way, so that number of multiplications required to compute the final results of that is final matrix multiplication is minimal. So another example for this particular case, consider a conformable multiplication sequence of 4 matrices now, A, B, C, D. You can fully parenthesize the multiplication in following ways. So this is one way. That means in this particular case, first we will multiply CD, then the B with the product of CD, then the A with the product of BCD final. Okay. In this particular case, we will first multiply BC, then we'll multiply the product of BC with D, and then the product of BC and D is multiplied with, that is A is multiplied with product of BC and D. Now in this particular case, instead of like that, BC will be multiplied, then A will be multiplied with the product of BC, and finally this particular product will be multiplied with D. Here AB will be multiplied, then CD will be multiplied, and their product will be multiplied. So you can see, now as we've moved from 3, where only 2 combinations were there, now as soon as we move to the 4, our number of combinations have moved to 6. As we move towards the 5, number of combinations will further explode. So the problem, you can see that the number of that is number of possible combinations, that is parenthesizations, may be very, very high. So how to find out and how to address this particular problem? So let us define this particular problem in a more formal way then. Okay, so what is our problem? How do we parenthesize a chain of matrices to minimize the cost of evaluating the product? Okay, so we will be just defining this chain. Okay, and the solution is use the dynamic programming approach to determine how to optimally parenthesize a matrix chain using the following steps. The first step is characterize the structure of an optimal solution, that is the recurrent solution. Recursively define the values of an optimal solution, then compute the values of an optimal solution and construct an optimal solution for computing information. And we will follow all these steps one by one as we go along in this particular example. So let's look into step 1 then. The step 1 is structure of an optimal parenthesization. Step 1 is structure of an optimal parenthesization. So let's look into, let's say, an optimal parenthesization of a chain matrix multiplication represented by how to multiply. Must break the product into 2 expressions. So first, this is the recurrent solution we are proposing. This whole solution, that is A1 to AN multiplication, will be product of 2 expressions, each of which is parenthesized or is a single array. So that is what ultimately that multiplication is going to lead to single array. A1 to AN multiplication is going to be leading to single array. Now we divide it into 2 problems. Let's say A1 to AK, right? So that is assume that breaks occurs at the position K. So in the optimal solution, the solution of the product A1 to AK must be optimal, right? That is what we are expecting. A1 to AK must be optimal. Otherwise, we could improve A1 by AN by improving A1 to AK. So what we are proving here, we are trying to prove that there exists the principle of optimality in this particular case, right? If we can prove that there exists principle of optimality, obviously what we can apply? The dynamic programming. All right. So moving on, that is, so we could improve AN by improving A1 to AK, but the solution to A1 to AN is known to be optimal. This is a contradiction. So read it again. Okay, so what we are saying, this product A1 to AK, let's say that this product is optimal. Okay, our result has to be optimal. That multiplications are, number of multiplications are optimal. So if it is not, A1 to AK are not optimal, then we can improve A1 to AN by improving A1 to AK. But the solution to A1 to AN is known to be optimal. Therefore, A1 to AK has to be optimal. The contradiction, and contradiction means thus the solution A1 to AN is known to be optimal. Then A1 to AK multiplication, that is between A1 till AK and AK plus 1 till AN, must be optimal. So this problem exhibits the principle of optimality. The optimal solution to product A1 to A1 of chain multiplication AN must be optimal solution of 2 subproducts. So now we can go for the subproduct, then we can go for the subproduct, further subproduct, and so on and so forth. So thus we can use dynamic programming. So in the first case, we are just trying to prove whether we can apply dynamic programming in this case or not, right? By proving the principle of optimality. And what we have used is the law of contradiction, right? Very simply, if we are multiplying A1 to AN, right, and it is optimal, this is an optimal way of finding the multiplication or optimal parenthesization, then A1 to AK also has to be optimal. If it is not, then we can always improve that multiplication. That is what the contradiction was, right? So let's move to the step 2 there, from there. So what is a recursive solution to this? So pick a sub-problem for determining the minimum cost of parenthesizing. So this particular thing is to be parenthesized. That is AI till AJ. All the matrices, we got to parenthesize that, right? And where I can vary from 1 till n. J can vary from n. Right. So terms to be used, which we will be using, Mij, which is the minimum number of scalar multiplications, right? Remember this particular term, Mij, because we would be using it in the complete algorithm, right? So minimum number of scalar multiplication needed to compute the matrix multiplication. That is our basis of determining. And this AI triple dot J means that is from I to J, multiplication of all the matrices from AI to AJ. That is the number of scalar multiplication needed to do so. And the second thing which we will be using will be the lowest cost, and what we actually need to determine is that M1 to N should be minimum, right? So M1, I has to be 1 and J should be N. If this is minimum, then all the sub-problems will also be minimum. Remember, our problem of dynamic programming starts from top down. So if you know the optimal solution, you know the sub-solutions. But other way around, we got to develop the algorithm, and that is what we are developing. All right? So this is what talking about the same matrix, right? So multiply require any cost. There is no cost. So that is the terminal condition. So the terminal condition when I equals to J, then the cost, that is Mi comma I, happens to be 0, right? So that problem is trivial. So what you can see is basically we A1 to A5. They have typical dimension 30 into 35, 35 into 15, 15 like that. You can see the 35 is there, right? So it is conforming. 15 is here, conformance. 5 conforming. So all the multiplications are conforming. Now what we need to determine is how do we multiply them so that the overall multiplication is achieved in optimal number of multiplication or minimum number of multiplication. So with this particular problem, and let us look into this particular thing. Okay, so now we move on to the recursive solution, right? So the optimal solution of AI till AJ must break less than J. Each matrix AI is Pi minus 1 into Pi. Now this is something which we need to understand. Okay, let's go to the example down here. Look into this example. So A1, what is the dimension of matrix A1? 30 into 35. A2, 35 into 15. So now, what is this P? P is basically representing the one of the dimension of the matrix. Okay, obviously we are going to multiply these matrices. So P0 is the lower bound or the lower that is dimension, that is 30. Okay, P0. And what is P1? 35. Now in this particular case, this is the lower one, right? So for A2, it is going to be Pi minus 1. For A2, Pi minus 1 becomes P1, right? So P1 is 35, you can see. And this 15 is coming here. So the second bound or the second order is what is the AI P1, A2 P2, A3 P3, A4 P4, like that. But the lower bound or the lower order is in one index down, the one array down. Okay, so the matrix is being represented. Matrix dimension is being represented with the help of array P, one dimensional array P, like, so P0, P1 forms the dimension of A1. So you can see 30 into 35, right? Similarly, P1 into P2 forms the dimension of matrix A2. P2, P3 forms dimension of A3, like that. Okay, so this is Pi minus 1 into Pi, right? So if I'm referring to A3, then P2, P3 determines A3, right? So you can see that this particular P is the basically what we are passing for matrix chain multiplication is going to be, we will be using P. And we are starting with P0 because A1 has a dimension P0 into P1. All right. So this is the way we are going to. Similarly, A2 has a dimension P1 into P2. So you can see 35 into 15 and so on. Now computing the matrix multiplication takes, so if I'm computing AI to AK, let's say if I say A1 to A3, that is one particular, and I'm wanting to multiply it with A4, A5, that is in one bracket. So what will be the product, what would be the size of this particular matrix? 5 into 20. And what would be the size of A1 till A3? 30 into 5, right? So this multiplication will require I minus 1, A1, that is 30, then 5 multiplied by 5, multiplied by the size that happens to be the last one, the J, 20. So like that we are going to compute the value of number of multiplications, scalar multiplications, whenever we are going to whenever we would be computing this particular stuff during dynamic programming. So the final effective the term which is the dynamic value which we will be computing, that is the minimum cost of computing matrix I to J is minimum cost of computing from I to K, right? And then K plus 1 to J plus the dimension of Pi minus 1, then the dimension of Pk, right? Pk happens to be this particular thing, for example, 5 in this particular case. So dimension of Pk, and finally dimension of Pj. That is the second dimension of Pj, the column value. So you can see the implication of this particular value. Okay, this is a very important term, and this we have derived from the previous example. And you will see as we move around, it will be becoming more and more clear as we move around. Now, how to compute the optimal cost? So we have reached that stage now. So let's look into the algorithm. So how many matrices we are trying to multiply? The length of P minus 1. Why length of P minus 1? We were starting with P0, right? So P0, P5 till P5, obviously length minus length of P, which happens to be 6, minus 1. So we are multiplying, that is 5 matrices in this particular case. But in general, this is the first step of initialization. Find the number of matrices which you want to multiply based on the value of P. You are passing just a single dimensional array P. So that P determines the number of matrices which we are trying to multiply. The second thing is that we need to declare M from 1 to n. So basically, if you are using C, then it will be like M n, the bracket close, comma n, like that you declare. But what it simply means is M is an array of size n cross n which stores the optimal cost. And S is a very important another array which is of the size n minus 1 to, and it starts, as far as J starts, from 2 to n for the value of K. So these two matrices are shown over here. And if you remember, when we started for I equals to when we say I from 1 to n, do MI is made as 0. Why? Because it is the same matrix. So now look into this particular arrays which we are drawing here. I is being represented over here. So this is the case. We are giving an example of 5 cross 5 matrix, right? So we are going it. For 5 multiplication of 5 this thing. So the value of P is going to be P0 to P5. Okay, and the value of I in this particular case, as per this particular convention, N is 5. So it is I's values are from 1 to 5. So are the J value from 1 to 5. On the other hand, for S array, we are from 1 to N minus. I values are from 1 to N minus 1. That's why it is from 1 to 4, right? N is 5. So N minus 1 is 4. Whereas J is starting from 2 to 5. So this is how it looks like. Why we are starting from J equals to 2, it will be becoming clear to you. And why we are just stopping from I 1 to 4, because bracketing once again. So that is what it will become clear as we go along with the computations. So let's look into the algorithm's next step. Now, what we want to do, our objective was to multiply arrays, right? So we have array A1, A2, A3, A4, A5. It's a binary multiplication. So what may be the first choice? If I multiply A1, A2, then A2, A3, A3, A4, A4, A5, right? Like that I can multiply, right? I'm not actually multiplying. I'm just determining where the cost may be the minimum, right? So our multiplication is going to be like that, okay? So T basically is the length of the chain, right? And the minimum length of the chain is going to be 2. After all, this is binary multiplication. So we are going to start with the length of 2. Then we will go to a length of 3, 4. And since we are dealing with just 5, that is 5 matrices in the chain. So ultimately, the 5 is going to be the maximum, right? So 1, 2, 3, not 1, 2, 3, 4, and 5. So these are going to be the length of the chain. And for each length of the chain, there will be multiple possibilities. Out of those multiple possibilities, obviously you will be requiring another index to determine those multiple possibilities. But not in the case of when we are having the chain size of 2. So let's look into the algorithm therefore. So for T, which moves from 2 to N, right, which is like the length of the chain. So it is going to be moving from 2, 3, 4 and 5 if we are taking the example of 5. Otherwise N is whatever is the number. Now what we are doing, for I, what we are repeating for from 1, the value of I is from 1, we will be starting from first. N minus T plus 1. What N minus T plus 1 is? N was 5, T is 2 plus 1. That means it is 5 minus 2 plus 1. That is 4. So the value of I will be 1 to 4 only, because we are doing multiplication of 2. And what we will be doing? We will be multiplying the value of J. J happens to be the second matrix with which you would have to multiply. So the value of J will vary from I plus T minus 1 only. So that means, so 2 minus 1 was what? 1. The value of I is going to be 1. So 1 plus 1, that is going to be 2. When I is 2, the value of this is going to be 3. When I is 3, the value of this is going to be 4. And then when I is 4, the value of J is going to be 5. So you can see 1 to 4, when it is 1, J will be 2. When I is 2, J will be 3. When I is 4, J would be 5. Right? So this is the way this particular multiplication has to proceed. Then the first thing which we need to do, so let's take first case 1 to 2. So I 1 comma 2, we are assigning a value infinite. We don't know that. So we are just assigning a value infinite. Now the number of times we are going to repeat k I to j minus 1. Now this is a very, very important stuff. Okay, j minus, so I 1 to, first in the first case, the value of k would be 1 to 2 minus 1, which is 1. So k will be only 1 to 1 only, right? And what we are computing is the cost of multiplication. This cost of multiplication is the same, the term which we have just defined in the previous slides, where mik, mk plus 1 comma j, and then pi minus 1, right? Because we are referring to this particular matrix, k, this value, and then pj, right? Pj is this particular term. So this is the multiplication which is going to determine us the cost. Now, if this cost is less than mij, which initially has been infinite, then we will replace I comma j with the q and si comma j with the value of k which has been used. Okay, and then we return, finally we return these matrices. So let's come back to this particular slide now. What we see in this slide, there are certain values, etc. Let's try to look into, just ignore these values. We are just having these 0 values. So how the values are going to be computed? Well, this was our matrix. So P0, P1, P2, P3, P4, P5, all are there, right? And this is how I was trying to define. So for I equals to 1, j equals to 2, this was our first thing. What I said was k is equal to 1 to j minus I, or k is equal to 1 to 1. Now it is very clear over here. So what is the value of 1? M, 1 to 2. What is the value of k? K is just 1. In this particular case, 1 to 1 means first k we are taking 1, and that is the only term in this particular case. Okay, so M11, right, replacing it into our expression, M11, k plus 1 to j, j was 2, so this is what you can see over here, M22 plus P0, 1 less than this, right, I minus 1 to P0, then that is P1, which is the value of k, right? And P2 happens to be the value of j. So you are multiplying that. Now what is P0, P1, P2? These are over here. P0, P1, P2. So actually we are multiplying A1 with A2. So when we are multiplying A1 with A2, it is 30 into 35 into 15. That is being represented with the help of the algorithm value. Okay. And this turns out to be 15,750. This is this particular term. What was I1, Mi? That is M1, J was 2, right? So M12 gets this particular value, which has been computed like this. And what was the value of K? It was 1. So this K value has been, in this particular case, what is I1, right? For I1 and j equals to 2. That is where we are starting. The value of K was 1. Okay. Now let's look into the second computation for 2 to 3. I equals to 2 and j equals to 3. Similarly, what you will observe, K goes from 2 to 2 only. The same results are over here. P1. Now you would be doing the multiplication of A2, A3. You're planning, right? So when you multiply A2, A3, what would be the size? A2, A3, basically 35 into 15 into 5, 35 into 15 into 5, P1, P2, P3, right? So this is P1, P2, P3. This is what the value is. This is 2625, and that is being. And what is the value of K? 2. Okay. Similarly, 750, the value of K for I equals to 3, 4 is going to be 3, like that. Okay. So these values are filled up. You can see these values of 265, 750, 1000 have been filled up, and 1, 2, for I equals to 2, 2 and 3. I equals to 3 and j equals to 4. I equals to 4, j equals to 5. So all these values have been filled up, right? You don't need to go beyond this in this particular case. So you can see why we had the smaller index smaller indexes in second matrix. Let's move on to t equals to 3. Now what you see, once again the same multiplication, but what you see, the I value will be from 1 to 3 only, and accordingly the value of j is going to be, when I is 1, j equals to 3, When I is 2, j equals to 4, I equals to 3, j equals to 5. So these three values are going to be filled up now. These three values are going to be filled up. And how those values are going to be computed? Now you are having two k's. Why? K is the value of I is 1, j is 3. The value of k is I to j minus 1. That means 1 to 2. Now for k equals to 1, okay, now what does it mean? Now you are multiplying three matrices together. So one possibility is when k equals to 1. That means A1 is separate and you multiply A2, A3. Or second one is when k equals to 2, you are multiplying A2, A3 first and then multiplying A3 with it, with the result. So this is what it means. And accordingly, the previously computed costs, okay, like 2625 and 23 was already computed, right? So 2625 was already there in the matrix. This M11 is 0, trivial. So 2625 we have already computed. And then what you are doing here, you are multiplying P0, P1, P3. What you are k equals to 1. So you are multiplying A1 with the product of A2, A3, which is 35 into 5, right? So you can see that values, right? That is why it is P1, P3. P0, P1, P3. So very important that you go through these particular terms. And the two values are being computed for k is equal to 1 and k is equal to 2. Now what we find, minimum of these is 7875. For what value of k? K equals to 1, right? So this S13 becomes 1. All right. Over here, once again, it is computed for both the values and the minimum values is found out. In this particular case, k equals to 3 has the minimum value, right? And in the last case, what you can see that minimum values has been found out and the k equals to 3. So you can say, you can observe that those values 1, 3, 3 values of S has been filled up over here, and the values, the minimum values has been filled up in this particular case. Moving on, we do the similar computation for the value 4. But what are the values of I and j? 1 to 4 and 2 to 5, just 2. But the values of k now are going to be at least k is going to be 1, 2, 3. So you have now three different k equals to 1, k equals to 2, k equals to 3. What way you are doing? Now you are multiplying A1 to A4, right? So one possibility is you multiply A1, you multiply in this k equals to 1, right? So k equals to 1, A2, A3, A4 you have multiplied. But whatever way you have multiplied, you have already got that particular result somewhere in M, 4375, right? But you are multiplying A1 with the product of A2, A3, A4 together. Okay, so this is the way it is going to be computed. And P0 into P1, right? P1 multiplied by P4, because A2, A3, A4 is going to bring a matrix of the size 35 into 10 only. So you are multiplying a matrix of 30 into 35 with a matrix of 35 into 10. Okay, so this is how you are going to compute the numbers. Automatically, algorithm is going to compute these numbers for you. And the value of k, out of these three, what you find? The minimum is this value, so which is value of k equals to 3. In the second case, the minimum values is 7125. The value of k even at this point is also 3. So you will get this is what we have filled up, 9 this thing, and accordingly these values are filled up. Finally, at the final step, what we are going to do, these values are going to be computed in a much simpler, using the value of, so you are computing from will be 1 to 5. So all this computation, this is the final computation. And in this final computation, what we have got, k is equal to 1 to 4. And all these values are computed, and finally overall minimum. Okay. And this is all the values of S has been filled up, right? So now we need to construct the optimal solution. We are able to find the minimum value, but we do not know how the parenthesization of those matrices are going to be performed. Okay, our overall matrix multiplication cost, optimal cost is 11,875, right? But we have not been able to know how that multiplication is going to be performed. So this is what is going to be determined with the help of S matrix. Now, for constructing the optimal solution, what we need to do is we need to write another or use another algorithm called print optimal parenthesis algorithm. And this particular algorithm is being shown in this particular case. Now, I have just for the sake of distinguishing, I have created two. This is the algorithm. I have created A and B because there are two calls. So this is called A, this is called P. Now, this is my S matrix. Okay. And we will start this particular stuff with I equals to 1 and J equals to 5. What it says, if I equals J, then print A, whatever I value is. Otherwise, print parenthesis. So you will print parenthesis. All right. Okay. This is going to print the first parenthesis. Now, as you move to this, okay, so what you are going to find? The value of this particular, at this point of time, when you pop S, I, okay, what is the value of S is this particular matrix. The value of I remains unchanged. I is 1. Sij. Sij happens to be 1, 5. So what is the value of 1, 5? 3. That means Sij is 3. That means our call is going to be I equals to 1, J equals to 3. Okay. So this is A call and this is B call for this. B call will come later. That's why the red color has been used. Next, from here, this A matrix will once again call A equals to A with the value of J equals. Now this is where 1. Now what is the value of this? A I comma J. Sij is 1, 3. Okay. 1, 3 happens to be 1, 1. So I becomes 1, J becomes 1. Okay. So that's where as soon as it becomes, then this value is going to be printed. So two parentheses, one because of this, another because of this. The third, it is going to print, it is I equals to J, so it is going to print A1. Then this particular call, once again, I is not equals to J, another parenthesis is printed. I becomes equals to J, A2 is going to be printed. I equals to A3 is going to be printed. Now this call is complete. This is complete. So a bracket close, print bracket close is going to be printed. Okay. Now this further, so it starts with B. Another, this A is also complete when this second AB is completed. So another bracket is going to be printed like that. So this is the call sequence what you can relate to. That is pop S15 is going to call 13, it is going to call 45, 45 is going to call 11, 13 is going to call 11, and 23 it is going to call 23, 33, and that is the way our brackets etc. are going to be printed accordingly. So this is the way. If we can just have a final look, so A2, A3 are going to be computed first. Then the result of A2, A3 is going to be will be multiplied with A1. Then A4, once this complete result is available, A4, A5 will be multiplied, and the result of A2, A1, A2, A3 is going to be multiplied by A. And relate that this and this actually had the big point for multiplication from the optimal solution. So this is the way this matrix multiplication is done. Let me just summarize what we have done in this particular session. Dynamic programming requires the problem to show the principle of optimality. Components of global optimum solution must themselves be optimal. The problem of chain matrix multiplication determines the sequence in which a chain of matrix multiplication should be performed, not the actual multiplication. The solution for matrix chain multiplication using dynamic programming requires two algorithms. We have studied both the algorithms. The first one determining the cost dynamically, and second finding the optimal parenthesized matrix multiplication, which is done recursive, which is a recursive algorithm. With this, I end this particular session. Thanks for being with me.